So we are going to continue down the path of probability. Things are going to get, like I said, the path is going to get a little bit windier on us now, all right? So far we have talked about and statements, which is what we did yesterday. And statements, when we have an and statement, we multiply probabilities. We've dealt with or statements, and or statements require us to use the addition law of probability. And when you do that, it matters if there's overlap or not, which occurs in the and. And so are they mutually exclusive or not? That is a problem. And now we're going to introduce another wrinkle to the idea of ands and ors and all that stuff, and that is dependent events. So we've already covered what it means to be independent. And we did that yesterday, right? We talked about independent events are things like flipping a coin and rolling a die. They don't matter to each other. But of course, if there's independent events, then there are things called dependent events. And this is where one event will be affected by another event occurring. For example, at the very beginning of probability lessons, I asked Gavin to do the Monty Hall problem with me. And he picked a door. And then before we asked him whether or not he wanted to switch doors, I opened another door. You see, me opening another door affected the probabilities that remained in the end. So that mattered. That was a dependent situation. If you were to, you've all seen those questions that are like, oh, a bag of Skittles has, this many reds and this many greens. What's the probability you pull a green out, right? Now, let's be real. You pull a green Skittle out of a bag of Skittles, or red, or whatever color you like, you're probably going to eat it. See, now if I ask you what's the probability of reaching in and pulling out another green one, those probabilities have been affected by the fact that you took one out and ate it. You changed the system when you did that, and that is a dependent event. So if an object is put back in the group before choosing again, we call that sampling with replacement. Those are independent. So I reach into a bag of Skittles. I pull a Skittle. I go, I wonder what the probability is that I pull out a green Skittle. I pull a Skittle out and go, neat. And I drop it back in the bag. And then I say, I wonder what the probability is that I pull out a green Skittle. Well, the answer is the exact same that it was a second ago. Those are independent events. But if you eat that green Skittle, that is sampling without replacement, and you have changed the system, which is going to be dependent. So two or more events are dependent if the occurrence of one of the events does affect the occurrence of the other events. Events are dependent if they are not independent. So you have to be one or the other. Systems are either independent or dependent. So events are dependent if they are not independent. And if A and B are dependent events, then the probability of A intersect B will still be the probability of A times the probability of B. But that will be the probability of B given that A has occurred. Does that make sense? Because you know A happening affected B. For example, I'm going to close my eyes, and I'm going to take that ball that Max had, and I guess a lot of you guys had, a little squishy stress ball. I'm going to close my eyes, and I'm going to throw it into the crowd as hard as I can. And the student that I hit is going to leave the room. And then I say, what is the probability that I hit 2 boys with 2 throws? With 2 throws. Well, here's the thing. When I threw that first ball, the probability is, 1, 2, 3, 4, 5, 6, 7, 8 of you in the room, and let's just say there's 20 of you. I didn't really count, so it'd be 8 out of 20, right? But if I hit you, bop, and Gavin had to leave, now the next one is not 8 anymore, it's 7, and it's 19, because there has also been a person removed from the system. So if I said, what's the probability of a boy and a boy, it would have been 8 out of 20 times 7 out of 19, because that was the probability that B happened given that A already occurred. That's how it works. A box contains 3 red, 2 blue, and 1 yellow marble. Just for, what does that give us? That gives us 6 marbles. Okay. You're going to pull 2 marbles from this box. It says create 2 different tree diagrams for this scenario, one that has replacement and one that has no replacement. Okay, so let's start there. Tree diagrams. What are they? Red, blue, yellow? Great. Let's go with replacement first. So this is, I'm going to say width, if you guys are cool with that. The width tree diagram. Write small, you don't have a whole lot of space. First event. How many different options did I have? Don't break your brains, guys. How many options did I have for the first one? No, 3. Because there could have been 3 different colors. It either could have been red, or blue, or yellow. These are my 3 possible events. This is the width replacement tree. So it doesn't matter which marble I pulled out. I'm going to put it back in the box. So that means when I go to pull the second one out, I'm going to get the exact same 3 branches that I started with. No, that's not yellow, that's blue. There. Now the without replacement tree diagram is a little more fun. Notice my tree diagram doesn't have any probabilities on it right now. And I kind of wrote this thing a little bit too small for me to squeeze my probabilities in there, so you guys will just have to bear with me. I am so sorry. I didn't give you enough space either. I am so sorry. First event, exact same 3 possibilities. Red, blue, yellow. Red, blue, yellow. So let's say I pulled that first marble out and it was red and I went, ooh, cool, and I put that red marble in my pocket. Do I still have 3 colors in the box? Yes. Yes, I do. Okay. Red, blue, yellow. All right, well, let's say that first marble I pull out was blue, and I go, ooh, blue, and I stuff that blue marble in my pocket. Do I still have 3 colors in the box? Yeah. Yes, I do. Red, blue, yellow. Now let's say that first marble that I pull out of the box was yellow, and I go, ooh, yellow, and I stuff that yellow marble in my pocket. Do I still have 3 colors in the box? No, I do not. This system has changed. Now there's only 2 colors left in the box. If that first marble was yellow, all that's left is red and blue. There's our tree diagrams. Part B. What? What's wrong, Gavin? What seems to be the issue?
That was
with replacement and without replacement. Yeah.
Okay.
Which part? Down here? Okay, let's say you reach into, look at up here. You reach into the box, and the first marble you pull out is yellow. You stuff it in your pocket, it's gone. There are no more yellow ones left in the box. Now, part B says find the probability of getting 2 different colors with replacement.
We have to know which one gets taken out?
No, it says with replacement.
Sorry.
Yeah. So part B, find the probability of getting 2 different colors with replacement. Well, you have 2 options. You can either figure out what the probability of each of the branches is that has 2 colors, and there's a lot of them, or you could figure out the probability of matching colors and just subtract that from 1. I would rather figure out the probability of matching colors and subtract it from 1 because I think it's easier. But that's me. I mean, it's up to you which one you want to do. I'm going to go with the subtraction method. I'm going to say the probability of, what was this, different colors? Is 1 minus the probability of matching. So I'm going to take away the probability that they match. Well, there are 3 different ways they could match. They could both be red. Well, what's the probability that one of them is red? Well, don't reduce.
4 out of 6.
3 out of 6. See, there are 3 red marbles in the bag. So the probability that they're both red, and you know what? I forgot, I was writing in black. Hold on, oh my gosh! Okay, I was writing in black for a reason, because I'm writing in color for my marbles. 1 minus. The probability they're both red is 3 out of 6 times 3 out of 6. Minus. Because there are 3 red marbles and there are 6 in the bag. Because this is with replacement.
Okay, you're just looking at the overall.
Yes, because you're putting it back.
I like the tree diagram. I was like, where's that?
No, I didn't write on the tree diagram because it's going to be too cramped. But this is the way the tree diagram would have looked. The probability that they're both blue, that is going to be 2/6 times 2/6. And then the probability that they're both yellow? No, with replacement. 1/6 times 1/6. Because it says you're pulling out 2. Find the probability of getting 2 different colors with replacement. So what I'm going to do, because that happens a lot of different ways, I'm instead going to find all the ways that they could have matched, which is not 2 different, and I'll subtract that from 1, and that'll leave me the probability that they don't match. And since it's 2 marbles, it's 2 things multiplied together, and they are independent events, so you just multiply them. So what does that give me? Gives me 1 minus 9/36 minus 4/36 minus 1/36. That should leave me 22/36. Yes? 22 out of 36. You can reduce if you want. 11/18. Neat, huh? So there's an 11 out of 18 chance that when you pull 2 marbles out back to back with replacement, that they're different colors. You see, because there were 22 ways that they were different, but there was only 14 ways that they matched. So it was easier to figure out the matching ways and subtract them. Now part C, it says find the probability of getting 2 different colors without replacement. Okay, we're going to do the exact same trick. I'm going to squeeze these words in here, part C. This is the same thing, but this is without replacement. So I'm going to do 1 minus the probability that they match without replacement. So what would my probability be? 1 minus, now let's talk about blues. What's the probability, red. What's the probability the first marble is red?
1 out of 3.
No, it's 3 out of 6.
Yeah.
Okay. Now, if you were to have removed that red marble, what's the probability the next one is red? 2 out of 5. Now we move on to the blues. What is the probability that the first marble I pull would have been blue? 2 out of 6. And if I did pull a blue one, what's the probability the next one is blue? 1 out of 5. What's the probability the first marble I pull is yellow? 1 out of 6. And if I pull that marble from the bag and don't put it back, what is the probability the next one is yellow? 0. You don't even have to say out of 5. Impossible. So don't even worry about it. What you get is 1 minus 6 out of 30 minus 2 out of 30. Is that 8 out of 30. So you get 22 out of 30, which reduces to 11 out of 15. There you go. That's the probability that you pull out 2 different colors without replacement, 11 out of 15. So it's a greater chance of that occurring. Why? Because you can run out of yellow marbles, which forces them to not match. That's why.
Wait. Why did you put it?
Ask, what's up? Why'd I put what?
Oh, my bad. I actually read the blue as the yellow because I'm retarded.
We're not going to be dropping hard R's.
So wait, so the 1 6 times 0 is just 0.
Yeah, it's just 0, so it doesn't count for anything. Because if you pull that first marble out and it's yellow, and you don't put it back, you can't pull another yellow out because it was the only one.
Yeah.
Without replacement. I just want you to know I assigned a question to you that I did with a tree diagram that was huge. So expect to be using tree diagrams in your homework.
Wait, is that the one that was like?
Why are you trying to do the homework early?
Wait, this?
Talking about tonight's homework, yeah.
Just kidding.
Okay.
There's no way I'm doing homework.
Okay. A box contains 4 red and 2 yellow tickets. All right, we have 6 tickets. 2 tickets are randomly selected from the box, one by one, without replacement. Find the probability that both are red. I'm going to do this one without a tree diagram because I can. So let's find the probability that both are red. It says without replacement. So what's the probability the first one was red? 4 out of 6. You don't put it back. What's the probability the next is red? 3 out of 5. No, you're good. So the probability that both of those things are red, you see I wrote it in red, is 12 out of 30. Since that's the end of the question, I'll just go ahead and reduce it because why not? That is 2/5. 40% chance that they're both red. How about that? Part B. It says find the probability that the first one is red and then the next one is yellow. Color-coded notes are fun. Well, what's the probability the first one's red? 4 out of 6. And what's the probability that the next one is yellow? 2 out of 5. Which is 8 out of 30 or 4 out of 15. So if this was a longer question and they might have something to do with each other, then I would probably not have reduced either one of those. Because I see a 12 out of 30 and I see an 8 out of 30. They have a common denominator already. So a lot of times if it's a longer question, I will not reduce. Just because common denominators. So even though it's a dependent situation, there's still common denominators. Calm yourself, Bria. I'm sure it's Gavin's fault, but still.
Definitely not. I have not produced it any time. Or training.
A bag contains 5 red and 3 blue marbles. We have 8 marbles. 2 marbles are drawn simultaneously from the bag. That means at the exact same time. Determine probability that at least one is red. Now, is this with replacement or without? How many events is it? No, it's technically 2 events because you pulled 2 marbles. Now, I know they happen at exactly the same time, but they are 2 events. So this is a without replacement situation. It says determine the probability that at least one is red. So that means either one could be red or both could be red. Well, I mean, I could find the probability that the first one is red and the second one's not. And then I could find the probability that the first one's not and the second one is. And then I could find the probability that they both are red. And then I could add all three probabilities. Or I could say, well, there's a lot of ways that could happen, but there's very few ways that it couldn't happen. Find the probability that at least one is red. That means it's not both blue. That's what that means. So what I want to do is I want to find the probability that you have at least one red. I'm going to say that is equal to 1 minus the probability of blue and blue. Because if they're both blue, that is the only time that you haven't satisfied the at least one red. So it's much easier to do. The probability that the first one is blue is 3 out of 8. And if I took out one of those blue ones, there are only 2 left, and there are only 7 marbles to choose from. So this is 1 minus 6 out of 56. So there is a 50 out of 56 chance that you get at least one red marble. Wow. That's a big, big number, isn't it? Is it 25 out of 28 if you felt like reducing it, but you don't have to? Do you see how much easier it is to work with the complement? Often the complement isn't easy. No, but often it is easier. Basically, you have to determine which one's going to require me to do more work, adding up all the ways it could happen or subtracting the ways it can't happen. Sometimes it's identical amount of work. Like in yesterday's example, and Ethan brought it up and I said, hey, I want to go ahead and talk about that with the class. It was an equal amount of work, I think. It just depends on which one you would prefer to do because they're both viable methods. And now we got to flip on to the back. Does the back have some rectangles that are shaded and stuff?
Yeah.
Good. I like that question. A hat contains 20 tickets numbered 1 through 20. If 3 tickets are drawn from the hat without replacement, determine the probability that they are all prime numbers. Woo. Okay, you know what we got to do? You know what we got to do, right? We got to list the prime numbers between 1 and 20. So here are the prime numbers between 1 and 20. 2, 1's not prime. 2, 3, 5, 7, 11, 13, 17, 19. That's it.
Shut up. Oh my god.
1 is not prime by definition because if 1 is prime, then you can do scary things like show that 2 equals 3. 1 is not prime.
4 equals 10.
1 is not prime by definition because it breaks mathematics if you say it is prime.
That's sad.
It allows you to do really, really bad things.
You like make it sound like it's illegal.
It is illegal.
He's like, that can't be legal.
It's not. It's not allowed.
Weapons in school legal.
0 does not equal 1.
Never heard.
There's your prime numbers. It looks to me like there are 1, 2, 3, 4, 5, 6, 7. There are 8 prime numbers. So it says determine probability that all 3 of them are prime. That's easy. Probability of prime and prime and prime. It's just multiplications. And just means multiply. Well, there were 8 to begin with. So what was the probability the first one was prime? 8 out of 20. Well, okay, say you pull the prime one out. What's the probability the next one's prime? 7 out of 19, yeah. And the probability the next one's prime? 6 out of 18. Holy cow, those are big, big numbers. Okay, tell you what I'm going to do. I'm going to call this 1/3. So I'm going to try to do this without a calculator. And I'm going to call this 2/5. 2/5. And that's it. That's all the reducing I could do. So it's going to give me 14 over 15 times 20 is 300. So it's 285.
Oh my god.
Ta-da!
He said, ta-da. you make it sound so nice.
Would you say that I just do that in my head? Yes, I did.
Couldn't you also do like 95 times 3?
Yeah, 95 times 3 is easy.
See the Japanese multiplication method?
No, but would you like me to tell you how I got 285 so fast?
Yeah.
It says 15 times 19, right? Okay, that's tough, but what's 15 times 2? So what's 15 times 20?
15 times 20 is
If 15 times 2 is 30, then 15 times 20 is 300. I didn't say 15 times 20, I said 15 times 19. So I just did 300 minus 15. I used the complement in order to do my multiplication.
You are a genius.
Not a genius, it's a math trick. It's Common Core mathematics.
I should have known that on my SAT. I'm gonna take one.
But so to do what he said, would you say 95 times 3? Yeah, you can either say 270 plus 15,
yeah.
because that's 90 times 3 plus 5 times 3, or you could say 100 times 3 minus 15. Or, yeah, I said that right. How did you get 90? No, how did you, no, what made you say 90? You said 90 times 3, why did you say that? Oh, because you did 5 times 19 was 90. Oh, okay, because 5 times 20 would have been 100, so you took 10. Oh, yeah, 95, yeah. But that would have required people to memorize that 5 times 19 is 95, and that used the same trick that I just said. You see? Because 5 times 20 is 100, so 5 times 19 is 95. Yeah, it is. Okay, here we go. Fun. Shh, shut up back there. Fun. Ah, yes. The age-old petunia question. Is petunias correct? Oh, they're just flower. Yeah, petunias. Okay. 2 boxes each contain 6 petunia plants that are not yet flowering. Box A contains 2 plants that will have purple flowers and 4 plants that will have white flowers. Box B contains 5 plants that will have purple flowers and 1 plant that will have white flowers. You're going to select the box by tossing a coin. And when you toss that coin, you're going to remove a plant from the box. What is the probability that the plant you pull will have purple flowers? Woo! So here's what I'm going to do. I'm going to use a tree diagram. I think that'll be the easiest way to explain why this is what it is. Tree diagram. Let's just assume it doesn't matter what you flipped, heads or tails. How many? No, I said it doesn't matter. How many options do you have for the first event? Well, the first event is which box you pulled. So there are 2 events. There is box A, and there is box B. There are 2 events. You flip the coin, and you either go to box A or you go to box B. Now, when you go to box A, there are only 2 options: white flowers or purple flowers. And if you went to box B, same thing: white flowers or purple flowers. Those are your only options. But we can figure out probabilities. You flipped a coin. What was the probability you were going to get box A? Or 1/2, right? So if it's 1/2 for box A, then it's 1/2 for box B. Notice they add up to 1. If you were to have gone to box A, what is the probability of pulling a white one? 4 out of 6. That means the probability that it was purple is 2 out of 6. But had you gone to box B, what is the probability that it would have been white? 1 out of 6, which means there are 5 out of 6 chances of getting a purple. The question says, you flip a coin, you pull a flower, what is the probability that the flower is purple? So what we have to do is find all the places where we would have ended up with purple, figure out their probabilities, and add them. So highlighter, just because it makes life easy. All the ways I could have had a purple.
I thought that the first, I'm confused.
Okay, well, there's only two ways I could have pulled purple flowers. Look, you flipped a coin, which made you choose a box. That's event A.
Oh.
Then you reach in the box, you pull a flower out. That's event B. Okay?
But then wouldn't, if you chose,
So the probability that you flipped a coin and chose a purple flower, you flipped a coin for box A and chose a purple flower, would be one, oh gosh, that's highlighter. Every stinking time. I feel like they knew it was going to happen and they didn't say anything. Is 1/2 times 2/6, or 2 out of 12, which we could reduce to 1/6, but let's just not yet, because you never know. And down here, the probability that we picked box B, and purple flower is 1/2 times 5/6, or 5 out of 12. And since this is an OR situation, because what we've done is we have found the probability of, you're going to like this, ready? Box A and purple, or box B and purple is. You see the 1/2 times 2/6, that's A and P. The 1/2 times 5/6, that's B and P. And since either one of those scenarios satisfies, I have to add them because there is no overlap. It's impossible to overlap. You just strictly add them. So there's 2/12 plus 5/12, which is 7/12, and that is why we do not reduce our fractions, because had we reduced that 2/12 to 1/6, we would have had to have bumped it back up to 2/12 before we could add them. Yes?
So you're saying that like the little thing is really saying that that's basically like if
That was what the question was actually asking for.
so if it's like if it's box A and it is also C, then you just add
Yeah.
B and C. Can't you just do that?
Well, that's what I did. But I'm saying why.
Okay.
Yeah, I was using set notation to show you that was what the question was asking you in words. But that's the set theory behind it. No, I don't want you just looking at it, because here's another thing that happened. The coin flip was 50-50 chance, but it didn't have to be. And that's the thing, it could have been a weighted coin, or it could have been a spinner with 3 shaded and 1 not shaded. Like, there's just all kinds of things like that. So what happened was, because it was a 50-50 chance, you're saying, couldn't I have just looked and seen that there was, how did you get 2 out of, how would you have just known it was 7 out of 12 just by looking? Oh, because there's 7 shaded. Yeah. So the only reason, yeah. No. Okay, that's why. I didn't want to say it in case that's not what you were thinking. I just wanted to clear it up. So, yes, there are 7 shaded, but it only worked out that way because we flipped a coin. So in my mind, I feel like it's a bad example. The textbook should have specifically said that it's a spinner or something, and because the flipping the coin kind of made it dumb. But it could be used for anything that's not equal probabilities of occurring. There you go.